We have previously discussed that radian measure is closely tied to that idea of a circle, where we have a circle of a particular radius, and we work with the arc length that is measured off on that circle. And we've talked about using our arc length formula, rewriting the formula as S equals R times theta. So in this section, we are actually going to work with a very specific circle that has a radius of 1. Because we're working with a radius of 1 unit, we call it the unit circle. If R is 1, and I'm looking at my formula here, if R is 1, then we could say that S, the arc length, is actually going to be now directly equal to the angle measured in radians. So, as we're evaluating our functions, remember that for our trig functions we always put in an angle, and now we're going to be putting in an angle measured in radians, and what we said before was that radians are basically just real numbers without a unit. So now we're doing a real number S, so it's just a number. It's represented by a directed arc on the unit circle, so it's the arc length, which is going to be equal to the central angle theta. So we could say S of some angle, which is just now a real number in radians, is equal to y. Now previously we said that sine of an angle is equal to y divided by r. Just said that the r, the radius of our circle, was going to be equal to 1. So if r is equal to 1, then now sine will be recognized as just y. And when we say y, what we're actually looking at is the y values of each of these points that actually lays on the unit circle. So here we have all of these ordered pairs, and every y value of those ordered pairs would be the sine value of that angle. So the sine of 30 degrees is 1/2. The sine of 45 degrees, square root of 2 over 2. So our actual sine values are just the y values of each of these points on the unit circle. Well, cosine theta was previously x over r, but now r is 1. So now cosine of our radian measure on our unit circle will just be x. So all of the x values of these ordered pairs that lay on the unit circle are actually our cosine values. So our unit circle is actually cosine of an angle, comma, sine of our angle when we're measuring in radians. Now tangent is not going to change because there's no r. So y over x, tangent is still going to be y over x. Now if sine is y, then cosecant of our angles in radians will be now 1 over y. Secant of s will be 1 over x, so they're still reciprocal. Cotangent also is still the reciprocal of tangent. Now the question would be, how do we get these particular points that are laying on the unit circle? To see where the points come from that lay on the unit circle, let's take our 30, 60, 90 triangle and let's place it at the center of our circle. So we have our 30-degree angle, and right now this 30, 60, 90 has a hypotenuse of 2. We want to shrink this down to where the hypotenuse is the same as the radius, and the unit circle has a radius of 1. So we're going to take the sides of our triangle and we're going to divide by 2. When we divide by 2, scales our triangle down to where we have a similar triangle that has a radius of 1. What we want to know is now, what is the point that lays on the terminal side of our 30-degree angle and intersects the unit circle? Let's find the x and y value of that point. Looking in the x direction, we see that from the origin to this point right here, we have a distance of square root of 3 over 2. And that is the x distance to the point, so the x value of that point would be square root of 3 over 2. In the y direction, we have a distance of 1/2. So we have the value of the x and y value of our point. The cosine value of this angle, pi over 6, or 30 degrees, was previously defined as x over r. Now that we know that we're dealing with a unit circle, r is 1. And if r is 1, cosine value becomes square root of 3 over 2. Notice that this is the same as the first coordinate of the point on our unit circle. If we're looking for the sine value, sine of pi over 6 is y over r. The y value is 1/2, and because we're working with the unit circle, r is 1. So we simply get sine is 1/2, which happens to be the second coordinate of the point on our unit circle. So what we see is that the first coordinate will always be the cosine value of that angle, and the second coordinate will always be the sine value of that angle. For 60 degrees, we can go through a similar process. Here we have our 30, 60, 90 triangle, and I have it on its side so that 60 degrees is right here. Across from the 60 degree angle, we have our square root of 3. Across from the 30 degree angle, we have a unit of 1, and the hypotenuse is 2 units. We're going to take the triangle and place it at the center of the circle. Right now it looks like the radius is 2, but we want to have the radius be equal to the unit circle, which is 1. So we want a radius of 1. Let's divide all 3 of the sides once again by 2. If we divide by 2, that'll scale our triangle down to where we have a radius of 1. And now we can see that we know the distance in the x direction and the distance in the y direction, so we can now label the point that lays on the terminal side of our 60 degree angle and also at the same time intersects our unit circle. So the distance in the x direction would be 1/2, and the distance in the y direction would be square root of 3 over 2. We know that the first coordinate would represent the cosine value of that angle, and the second coordinate would represent the sine value of that angle. Now we will take our 45, 45, 90 special triangle, which right now has a hypotenuse of square root of 2. We will place that at the center of our circle, and we want to make the radius be 1. So we will take the square root of 2 and divide it by the square root of 2. So we will take our special triangle and divide all sides by square root of 2. Square root of 2 divided by 2 is 1. And we have the other sides at 1 divided by the square root of 2. So we will rationalize these two fractions. So now our triangle is scaled down to have a radius of 1, and the x distance is the square root of 2 over 2, which is the same as the y distance. So we know that the value of the point that intersects the unit circle and lays on the terminal side of 45 degrees would be the square root of 2 over 2, comma the square root of 2 over 2. And the first coordinate, of course, would be the cosine value of 45 degrees, or pi over 4, and the second coordinate would represent the sine value of 45 degrees, or pi over 4. You should be able to label each point of our unit circle with the degree measure, the radian measure, and also the point that intersects the terminal side of the angle and the unit circle. Let's look at our quadrantal angles. Here we have 0 degrees, 90 degrees, 180 degrees, and 270, and then back to 360. We have discussed the radian equivalent of each of those angles: 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now let's look at our 30-degree reference angle family, or our pi over 6 reference angle family. Here we have 30 degrees, 150 degrees, 210 degrees, and 330 degrees. Each of these angles has a reference angle of 30 degrees. Each of them is part of the pi over 6 family. Here we have pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Here's our 45-degree reference angle family. We have 45 degrees, 135 degrees, 225 degrees, and 315 degrees. The pi over 4 family is the radian equivalent of the 45-degree reference angle family. We have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 as part of our pi over 4 reference angle family. And we have one more. We have our 60-degree reference angle family. 60 degrees, 120 degrees, 240 degrees, and 300 degrees all have a reference angle of 60. And in the radian equivalent, that's our pi over 3 family. Pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So here's all of our degree measures and also their radian equivalents. Now let's look at the points that lay on the terminal side of each of these angles and also intersects the unit circle. For pi over 6 or 30 degrees, we have seen that the x-coordinate would be square root of 3 over 2 and the y-coordinate would be 1/2. We know that the first coordinate represents the cosine value of that angle and the second coordinate represents the sine value of that angle. Because we're looking at the 30-degree reference angle family, we know that the sine and cosine values will be the same for each of these angles, except changing the signs of those values based upon the quadrants. So when you look closely at our 30-degree angle family, reference angle family, or our pi over 6 reference angle family, you can tell that each one of these points has the same first coordinate and the same second coordinate, except changing signs based upon the quadrant. Let's do the same thing for our pi over 4 or our 45-degree reference angle family. We know that the point that lays on the terminal side of the 45-degree angle would be square root of 2 divided by 2, comma, square root of 2 divided by 2. Because we're looking at our reference angle family, each of those angles that has a reference angle of 45 or pi over 4 will have exactly the same first coordinate and second coordinate, except changing signs based upon the quadrant. 60 degrees has a point on the unit circle of 1/2, comma, square root of 3 over 2. So when we look at the 60-degree reference angle family, we see that each of those points has exactly the same x and y values, except changing signs once again based upon the quadrant. Our quadrantal angles have exactly the same points that we have always used for the quadrantal angles. So we have 1, 0, 0, -1, -1, 0, and 0, -1.